Hi there, and welcome to Science Sleep, where quiet curiosity meets peaceful rest. Tonight, we drift into a softer corner of the cosmos, a place where stars almost came to life, but never quite found their flame. The stars that never were, failed stars floating in the dark. Together, wander through the dim, gentle spaces where these almost stars drift in silence, too small to shine, too heavy to be forgotten, carrying the quiet glow of what they could have been. Trace the soft physics that shape them, the delicate boundaries between planets and stars, and the calm, dark oceans of gas where they float. Ancient, patient, and unseen. So breathe slowly. Let your mind settle like starlight sinking into night, and allow Science Sleep to guide you into the peaceful mysteries of the stars that never ignited, quiet, hidden, and forever drifting in the dark. The universe is a quiet ocean of light and shadow. Its vastness stretches beyond the reach of imagination. Within this immensity, countless stars burn with powerful radiance. Yet between these shining beacons lie other objects, faint and hidden. They are the stars that never fully came to be. They are the failed stars, floating endlessly in the dark. Scientists call them brown dwarfs. These objects inhabit a strange space between planets and stars. They are too massive to be planets, yet they are too small to ignite like true stars. Inside their cores, the fusion of hydrogen never begins. Without fusion, they remain dim and cold compared to the stars that shine. The story of brown dwarfs begins in the same way all stars are born. A giant cloud of gas and dust collapses under its own gravity. As the cloud contracts, it spins and grows denser. At its center, a protostar begins to form. Heat rises as the material compresses. The temperature climbs toward the threshold required for nuclear fusion. In normal stars, this process continues until the core becomes extremely hot. Hydrogen atoms fuse into helium. The fusion releases energy. The energy radiates outward, pushing back against gravity. A stable star is born from this delicate balance. But sometimes the balance never forms. Sometimes the mass of the collapsing cloud is too small. The core cannot reach the temperature needed for hydrogen fusion. Even with gravitational pressure, the heat is not enough. The protostar flickers but never ignites. It becomes a failed star. A failed star is not a failure in the emotional sense. It is a natural outcome of cosmic evolution. These objects contribute to the structure of our galaxy. They add mass to the hidden skeleton of the Milky Way. They drift silently, almost invisible, yet always present. Brown dwarfs are often described as twilight objects. They glow faintly in infrared light. To human eyes, they appear as soft, ghost-like embers. Their temperatures are cool compared to stars. Some are barely warmer than a cup of tea. Others are colder than the human body. Because they emit so little visible light, brown dwarfs are extremely difficult to find. For much of human history, they were only theoretical objects. Astronomers suspected they existed, but no one had seen one. Detecting them required new tools and new wavelengths of observation. Only with infrared telescopes did these hidden worlds finally reveal themselves. The first confirmed brown dwarf was discovered in 1995. Its name was Teide 1. It was found in the Pleiades star cluster. Its discovery confirmed decades of predictions. It opened a new frontier in the study of stellar formation. The universe contains far more failed stars than once believed. Some astronomers think brown dwarfs may be as common as stars. They may even outnumber stars in our galaxy. If so, the night sky is filled with far more dark wanderers than bright suns. They linger in the void like forgotten sparks. Their silent presence shapes the gravitational landscape of the cosmos. Brown dwarfs range in size and temperature. Some are large and faintly luminous. Others are small and nearly invisible. Their masses typically fall between 13 and 80 times that of Jupiter. Below 13, Jupiter masses. An object becomes a planet. Above 80 Jupiter masses, it becomes a true star. Brown dwarfs do engage in a form of nuclear fusion, but the fusion is weak and limited. They fuse deuterium, a heavier form of hydrogen. This occurs only for a brief time in their early lives. Once the deuterium is exhausted, fusion ends. The object cools slowly over billions of years. Because brown dwarfs cool over time, they reveal their ages by their temperatures. A young brown dwarf is relatively warm. An old brown dwarf is cold and faint. Some ancient brown dwarfs may now be only slightly warmer than the cosmic background. These objects drift through space like frozen cinders. They shine only in the faintest infrared whispers. The darkness of a brown dwarf does not make it lifeless. Their atmospheres are chemically dynamic. Some have clouds of mineral dust. Others have clouds of molten iron droplets. Still, others have weather systems filled with methane and ammonia. These atmospheric features shift over time, like slow, alien storms. The rotational speeds of brown dwarfs can be extreme. Some spin in only a few hours. This rapid rotation shapes their clouds into bands. It stirs their atmospheres with powerful winds. It sends waves of heat rising and falling across their surfaces. Even without light, they have internal rhythms. Many brown dwarfs have companions. Some orbit stars. Others orbit each other in binary systems. Pairs of failed stars can drift through the void as gravitational partners. Their mutual pull binds them for billions of years. Together, they form small, dark families in space. Brown dwarfs do not remain the same throughout their existence. They evolve quietly over time. At first, they are warm and faintly luminous. Then they cool as their internal heat radiates into space. Eventually, they reach temperatures similar to planets. They become nearly indistinguishable from giant gas planets like Jupiter. In fact, some scientists describe brown dwarfs as super Jupiters. This term emphasizes their planetary properties, but their origin stories set them apart. Planets form in disks around young stars. Brown dwarfs form from direct gravitational collapse. Thus, they are planetary in appearance, but stellar in birth. The boundary between planets and brown dwarfs is a fuzzy line. Nature does not always follow human categories. The universe blends properties rather than dividing them sharply. Failed stars are a reminder of this cosmic fluidity. They occupy the in-between spaces of existence. They blur the edges of how we define celestial objects. Brown dwarfs influence their surroundings through gravity. Their mass helps shape the orbits of nearby objects. They can disrupt planetary systems if they pass too closely. They can tug on stars and cause subtle motions. These motions reveal their presence to astronomers. Even unseen, they leave gravitational fingerprints. Failed stars are scattered throughout interstellar space. Some lie close to the Sun. The nearest known brown dwarf system is Lumen 16. It sits just over 6 light-years away. It consists of 2 brown dwarfs orbiting each other. Their combined glow is barely detectable without infrared instruments. The idea of failed stars drifting near the Sun is both mysterious and calming. They pose no threat. They drift silently, indifferent to our existence. Their quiet presence reflects the stillness of the universe. In their darkness lies a peaceful stability. They are the sleepers of the cosmos. Objects like brown dwarfs help astronomers understand star formation. They are the low-mass outcomes of the stellar creation process. By studying them, scientists learn why some protostars become suns. They learn why others fade before they shine. The story of failed stars reveals the delicate dance of mass, heat, and pressure. It tells us how stars succeed or falter in their birth. Brown dwarfs also help us understand the distribution of matter in the galaxy. They may be part of the missing mass astronomers have long searched for. Their abundance could explain some gravitational anomalies. Their darkness makes them hard to count. Yet, their influence is unmistakable. Like hidden stones beneath a calm lake, they shape the currents around them. Finding brown dwarfs requires advanced instruments. Infrared detectors are essential. These wavelengths reveal heat rather than visible light. Brown dwarfs emit most of their energy in the infrared. Their glow is subtle but detectable with the right tools. New telescopes have expanded our ability to find these objects. The James Webb Space Telescope is particularly useful for studying brown dwarfs. Its sensitivity to infrared wavelengths is unmatched. It can measure the temperatures and compositions of failed stars. It can detect their clouds, storms, and chemical signatures. With JWST, the hidden worlds of failed stars become clearer. They emerge from the darkness as detailed scientific subjects. Despite technological advances, many brown dwarfs remain undiscovered. Their faint light blends with the background. Their small size makes them difficult to differentiate. Some may be drifting between stars without any nearby companions. These solitary wanderers are the loneliest objects in the galaxy. Their paths trace silent arcs through the interstellar sea. The concept of failed stars invites reflection. They represent an alternative path of formation. They teach us that the universe is not composed only of brilliance. Darkness also plays a role in cosmic structure. What does not shine still contributes to the whole. What does not ignite still has a place in existence. This balance mirrors life itself. Not everything must blaze with intensity. There is value in quiet presence. There is meaning in subtlety. The universe contains both the radiant and the muted. Each has its own purpose and story. The sleep-inducing nature of failed stars comes from their tranquility. They do not roar with fusion. They do not erupt with flares. They simply drift, cooling slowly, unchanged for eons. Their existence is a whisper compared to the shout of a star. Yet, in that whisper is a kind of cosmic peace. Their slow cooling process allows them to maintain internal heat for billions of years. They radiate warmth gently into the void. This warmth is the last remnant of their collapsed origin. It fades gradually, like a dying ember, but it persists far longer than expected. Their longevity makes them peaceful companions of the galaxy. Some brown dwarfs have satellites. These satellites may be rocky worlds or gas giants. The relationship between a failed star and its planets is intriguing. The planets orbit a faint central object. Their skies are dim and dusky. Their environments are shaped by infrared rather than visible light. If life could exist around a brown dwarf, it would be adapted to darkness. It would sense infrared glows instead of daylight. Its rhythms would follow the warmth of a faint ember star. Such worlds are hypothetical but fascinating. They challenge our ideas of habitability. They broaden the possibilities of where life might exist. Even in their failure to ignite, brown dwarfs hold scientific beauty. They show the diversity of cosmic outcomes. They represent an intermediate stage between planet and star. They broaden our understanding of what a celestial object can be. They teach humility by showing us that nature does not follow strict categories. The cosmos prefers gradients over absolutes. The darkness of brown dwarfs inspires sleep. It reminds us of night and stillness. It evokes the quiet landscapes of dream. These failed stars drift in eternal slumber. Their low temperatures and gentle glow resemble a resting heartbeat. They embody the softness of cosmic night. Their slumbering presence offers a form of cosmic reassurance. They exist without urgency. They drift without ambition. They cool without resistance. Their entire existence is a gentle descent into quietness. This makes them perfect companions for a peaceful night's rest. In the early universe, brown dwarfs may have formed more frequently. At that time, gas clouds were more turbulent. Their fragmentation produced objects of many sizes. Some fragments became massive stars. Others became smaller, cooler bodies. These early failed stars still drift through space today because they cool so slowly. Old brown dwarfs carry the memory of ancient times. They are relics of the galaxy's youth. Their temperatures reveal their age. The oldest ones are the coldest. These ancient brown dwarfs may hold clues about the early Milky Way. Studying them helps reconstruct the galaxy's history. The atmospheres of brown dwarfs undergo complex chemical reactions. At higher temperatures, clouds of iron and silicates can form. As these objects cool, the clouds dissipate. Methane begins to appear. Ammonia can emerge as the temperature drops further. Each stage of cooling reveals a new chemical environment. Astronomers classify brown dwarfs into spectral types. These types range from M, L, T, to Y. M dwarfs are the warmest and closest to true stars. L dwarfs show prominent metal oxide features. T dwarfs display strong methane absorption. Y dwarfs are the coldest and faintest of all. Y dwarfs have temperatures similar to Earth's atmosphere. Some may be only a few tens of degrees Celsius. They are among the coldest free-floating objects ever discovered. Their infrared glow is extremely dim. Finding them requires sensitive space telescopes. They are the epitome of failed star cooling. Because white dwarfs are so faint, they almost blend into the cosmic background. They are like shadows drifting between stars. Their discovery is a triumph of modern astronomy. They prove that even the coldest, faintest objects can be found. They remind us that the universe is full of hidden wonders. Much of existence lies just beyond our senses. Failed stars also challenge our understanding of planetary formation. Some brown dwarfs have disks of dust around them. These disks resemble the early stages of planet-forming systems. This raises questions about whether planets might form around failed stars. Such planets would orbit in darkness rather than light. Their climates and chemistry would be unlike anything around ordinary stars. A planet around a brown dwarf would not experience traditional daylight. Instead, it would receive heat in long, soft infrared waves. Its sky might have a perpetual twilight glow. Clouds would appear muted and shadowy. Temperatures could vary depending on the brown dwarf's age. Younger brown dwarfs could warm their planets more effectively. Over time, as the failed star cools, its planets would also cool. Their atmospheres might freeze. Their oceans might turn to ice. Their surfaces might become quiet and still. These worlds would slowly fall into deeper darkness. Their evolution would mirror the cooling of their failed star. Failed stars are not rare cosmic accidents. They are a natural part of star formation. In many ways, they represent the lower boundary of the stellar family. Their existence helps define what a star truly is. They mark the transition from stellar processes to planetary processes. They inhabit the threshold between the two. This threshold is scientifically fascinating. It is where nuclear physics, gravity, and chemistry intersect. It is where heat becomes insufficient to sustain fusion. It is where mass is too low to generate stellar pressure. It is the place where stars fall short of ignition. Yet, it is not a place of failure, but of transformation. For astronomers, studying brown dwarfs is like studying incomplete stars. They reveal what is necessary for a star to shine. They expose the limits of fusion. They show how gravity alone cannot always create fire. They illustrate the fine line between light and darkness. They embody the fragility of stellar birth. Many brown dwarfs have strong magnetic fields. These magnetic fields produce radio emissions. These emissions reveal their internal processes. Even in their dimness, they create magnetic storms. These storms are weaker than those of stars. Yet, they are intense compared to planets. The magnetic activity of brown dwarfs fades as they cool. In young brown dwarfs, magnetism may be strong. In older ones, it becomes weaker with time. This magnetic evolution parallels their thermal evolution. Both processes quiet down as the object ages. The older the dwarf, the calmer it becomes. Failed stars rotate rapidly. Their rotation can be faster than that of true stars. This rotation influences their weather patterns. Bands of clouds wrap around their equators. Storm systems form and dissolve in slow cycles. Their atmospheres shift like quiet, swirling shadows. Some brown dwarfs exhibit brightness variations. These variations come from rotating clouds. As cloud layers move, they change the amount of infrared light emitted. This produces a gentle pulsation of brightness. It is like the soft rhythm of a sleeping creature. The object glows, dims, and glows again. In this way, brown dwarfs seem to breathe. Their light gently rises and falls. This subtle variability adds to their hypnotic nature. They seem to pulse with a slow cosmic heartbeat. Their rhythms are calming to study. Their patterns resemble the serenity of natural cycles on Earth. Failed stars may live longer than the universe itself. Because they do not burn fuel rapidly, they change very slowly. A brown dwarf can exist for trillions of years. Its cooling is gradual and peaceful. It does not explode like a massive star. It fades rather than dies. This fading is a gentle decline into darkness. There is no violent end. No supernova eruptions. No collapse into a black hole. Just a slow loss of heat. A peaceful drift into eternal cold. Such an existence makes brown dwarfs some of the most stable objects in the universe. Their lifespans far exceed those of stars. Their tranquility is unmatched. They persist through cosmic eras. They outlive galaxies as we know them. They watch the universe evolve around them. The sheer longevity of failed stars has philosophical implications. They hint at the far future of the cosmos. In a time when all stars have burned out, failed stars will remain. They will continue to drift in silence. They will hold the last remaining warmth. They will be the embers of a fading universe. Even now, their presence is subtle. They do not dominate the sky. They hide in the spaces between brighter objects. They weave through the galaxy like soft threads of shadow. Their movements are unhurried. Their existence is understated. This understated presence makes them ideal subjects for meditation. Imagining failed stars helps quiet the mind. Their darkness invites calm. Their stillness invites rest. Their slow cooling mirrors the process of falling asleep. As the object cools, the mind cools with it. They remind us that not everything must shine. Not everything must burn brightly. Some things exist quietly and meaningfully. Some things unfold slowly and softly. Failed stars embody this softness. They float peacefully, with no need for brilliance. Because brown dwarfs emit mostly infrared light, they are invisible to the naked eye. Looking up at the night sky, you see stars, planets, and galaxies. But you do not see the multitude of failed stars drifting among them. Their invisibility adds mystery to the cosmos. It means the sky is fuller than it appears. It means the universe holds more than light alone reveals. Astronomers estimate that for every bright star we see, many more brown dwarfs wait unseen. The galaxy may be teeming with them. They are the hidden majority of stellar-like objects. They form a dim population beneath the visible structure of the Milky Way. Their gravity binds parts of the galactic disk. Their mass shapes the galaxy's rotation. In this sense, failed stars act like cosmic anchors. They stabilize regions of space. They contribute to the galaxy's gravitational harmony. Their quiet presence supports the luminous stars. They are the invisible framework beneath brightness. They are the silent partners of creation. Because brown dwarfs vary in temperature, they are sometimes compared to different stages of burning charcoal. Warm brown dwarfs are like glowing coals. Cool brown dwarfs are like embers fading to gray. The analogy highlights their elemental simplicity. They are objects defined by heat and its slow dissipation. They are the cosmic equivalent of a fire that never quite ignited. Failed stars also raise questions about how we define success in nature. If a star does not shine, is it incomplete? Or is it simply following a different evolutionary path? Nature does not judge outcomes. Every object plays a role. Every path contributes to the whole. Brown dwarfs demonstrate this idea beautifully. Their existence enriches the diversity of the universe. They show that cosmic evolution is not binary. It is not a choice between star or planet. It is a continuum. They inhabit the gradient between extremes. Their faint glow also teaches us patience. Finding them requires time. Studying them requires sensitivity. Their details reveal themselves slowly. Their secrets unfold quietly. They reward stillness and careful observation. As they cool, their atmospheres become more complex. Molecules form in the cooler layers. Strange chemical reactions occur. Condensates appear and disappear with temperature changes. Their clouds shift like dreamlike landscapes. Their skies evolve in slow, mesmerizing cycles. Some brown dwarfs may have rings. These rings could form from leftover debris. They might resemble the rings of Saturn, but colder and darker. Such rings would be nearly invisible. Only infrared observations might detect them. If they exist, they add grace to the failed star's appearance. The concept of ringed failed stars inspires imagination. Their silhouettes drifting through space would be serene. The faint glow of the brown dwarf would outline the rings softly. This imagery suits the dreamlike nature of these objects. They are quiet dancers in the cosmic dark. Their movements are slow and fluid. Failed stars can be born alone, or they can be born in clusters. In clusters, they drift with other stars. They share a common birthplace. Their paths diverge over time. Some remain near their siblings, while others wander away. Their wandering is guided by gravity. They follow gentle arcs through interstellar space. Their journeys are long and uneventful. They encounter few obstacles. They travel through clouds, between stars, and across empty voids. They are cosmic nomads. Their nomadic nature enhances their mystique. They do not depend on a parent star. They are free-floating objects from birth. They carry their own faint warmth. They move independently through the galaxy. They embody solitude without loneliness. Many failed stars reside in binary or multiple systems. In a binary system, two brown dwarfs orbit each other. Their gravitational bond is steady and enduring. Their shared journey offers stability. They drift together as companions. Their relationship is simple and profound. When a brown dwarf orbits a star, the system becomes even more interesting. The star's light illuminates the failed star faintly. The brown dwarf adds gravitational influence to the system. Its presence can affect planetary orbits. It can reveal itself through slight stellar wobbles. These subtle effects are keys to discovery. Failed stars challenge our instruments. Their faintness pushes the limits of detection. Their infrared signatures blend with background noise. Yet, astronomers continue to find them. Each discovery expands our understanding. Each detection adds another piece to the cosmic puzzle. Their diversity keeps research exciting. Some brown dwarfs are warmer than expected. Others are colder than predicted. Some have unusual chemical signatures. Others show unexpected atmospheric patterns. Each one is a unique experiment of nature. As we observe more failed stars, we refine our models. We learn how gas clouds collapse. We learn how mass determines destiny. We learn how temperature shapes evolution. The study of brown dwarfs deepens our knowledge of stellar physics. It strengthens the foundation of astrophysics. Failed stars also help calibrate instruments. Their faintness tests the limits of sensors. Their infrared glow is ideal for fine-tuning detectors. They serve as benchmarks for low-light observations. In this way, they silently support future discoveries. They act as stepping stones for technological progress. Their role in cosmic evolution is understated but essential. Failed stars act as quiet contributors to the galactic ecosystem. They occupy the lower mass end of the stellar distribution. Their existence ensures that not all collapsing gas becomes luminous. They moderate the star formation process. They prevent excessive fragmentation from producing only massive stars. By providing a natural limit, they balance the population of stellar objects. They help maintain the distribution of mass in galaxies. This distribution affects how galaxies rotate. It influences how stars cluster and drift. It shapes the structure of spiral arms. It determines the gravitational harmony of the Milky Way. In this way, failed stars are silent architects of galactic form. Their gravity shapes the motion of surrounding stars. They help stabilize star clusters. They subtly guide the evolution of stellar populations. They are small but influential, dark but essential. Understanding failed stars also informs our search for exoplanets. Some brown dwarfs host planets. These planets are easier to detect because their primary is faint. The contrast between planet and brown dwarf is less extreme than with bright stars. This allows instruments to capture planetary signatures more clearly. It opens new avenues for exploring planetary diversity. Planets orbiting failed stars experience unique environments. Their climates are shaped by long wavelengths of infrared radiation. Their days and nights might not resemble ours. Their ecosystems, if they exist, would evolve under dim skies. They would adapt to gentle warmth rather than fierce sunlight. Their worlds would be colder, quieter, and more serene. Imagining life on such planets sparks curiosity. What forms could survive in low light conditions? Would they sense heat rather than light? Would their biology rely on infrared energy? Such speculation encourages deeper scientific exploration. It expands the scope of astrobiology. Failed stars also intersect with the study of dark matter. For a time, some astronomers wondered if brown dwarfs contributed significantly to dark matter. These objects are faint and hard to detect. They seemed like possible candidates for missing mass. However, observations revealed that they are too scarce to account for dark matter fully. Still, they add to the baryonic matter budget of galaxies. Their gravitational role is subtle but measurable. They influence stellar motions in the vicinity. Their presence can explain certain orbital patterns. They alter the distribution of low-mass objects. They contribute to the invisible mass of the galaxy. In this way, they play a role in the cosmic structure puzzle. Failed stars remind us that the universe is not filled with brilliance alone. Much of its content is muted and hidden. Darkness dominates over light. Silence outweighs noise. Calm outweighs intensity. Yet all these qualities are part of cosmic beauty. Studying brown dwarfs is like studying shadows. They require patience to understand. Their signals are faint and delicate. Their details emerge slowly. Their characteristics reveal themselves over time. They reward careful observation. Their faint glow is often compared to the dying light of a candle. This analogy captures their aesthetic nature. They are embers that never became flames. Yet their glow carries meaning. It symbolizes endurance rather than brilliance. It represents quietness rather than spectacle. In their atmospheres, complex chemistry unfolds. As temperatures drop, different molecules dominate. At higher temperatures, metals vaporize. Iron clouds form and dissipate. Silicate particles drift in the upper layers. These mineral clouds glow faintly in infrared light. As brown dwarfs cool, metal clouds rain downward. Methane begins to appear in their spectra. This marks their transition into cooler spectral types. Cloud layers reorganize. Chemical reactions slow down. The entire object enters a calmer phase. At the coldest temperatures, ammonia signatures appear. This marks the emergence of white dwarfs. Their atmospheres resemble those of giant planets. Their chemistry is dominated by slow, deep processes. Their clouds are thin or absent. Their infrared glow is soft and subtle. White dwarfs represent the quietest stage of failed star evolution. They are the universe's ultimate sleepers. Their temperatures are only slightly above those of their surroundings. They drift with almost no internal storms. Their atmospheres move sluggishly. Their light flickers gently, like distant embers. Finding white dwarfs is extremely challenging. They require sensitive infrared surveys. These surveys must filter out background noise. They must search for the faintest whispers of heat. Astronomers use space telescopes to overcome atmospheric interference. Even then, detection is rare and precious. Each discovered white dwarf is a treasure. It pushes the boundary of what we can observe. It teaches us more about low-temperature physics. It reveals new stages of cosmic cooling. It expands our catalog of stellar-like objects. It humbles us with its subtlety. Studying failed stars teaches us to appreciate nuance. Their characteristics are not obvious. Their light does not scream for attention. Their signals require interpretation. Their nature is discovered indirectly. This process encourages deeper thinking. Brown dwarfs also challenge our expectations about size. Although they are small compared to stars, they are enormous compared to planets. Many are similar in size to Jupiter, yet they are far more massive. Their density is much greater. Their gravity is much stronger. This similarity in size between planets and brown dwarfs raises interesting questions. Why do objects so different in mass have similar radii? The answer lies in electron degeneracy pressure. This is a quantum mechanical effect. It prevents matter from compressing beyond a certain point. It stabilizes brown dwarfs against gravitational collapse. Electron degeneracy is the same principle that supports white dwarfs. In both cases, quantum mechanics defines the size of the object. This creates a unique situation where adding mass does not significantly increase size. Thus, a brown dwarf can be many times more massive than Jupiter, but only slightly larger. This shows how strange and beautiful physics becomes at high pressures. It demonstrates the harmony between gravity and quantum mechanics. Brown dwarfs also spin rapidly due to conservation of angular momentum. As the protostellar cloud contracts, it spins faster. This rapid rotation persists for billions of years. It shapes the object's atmosphere. It stretches storms into elongated patterns. It creates zones of turbulence that evolve slowly. The rotation periods of brown dwarfs can be extremely short. Some complete a rotation in only a few hours. This is far faster than most stars and planets. It makes their weather dynamic and complex. Yet, despite this motion, their overall evolution remains calm. Their cooling is unaffected by rotation. Failed stars also provide laboratories for studying extreme atmospheric conditions. Their temperatures cover a wide range. Their pressures are immense. Their chemical processes are exotic. These environments cannot be replicated on Earth. Thus, they expand our understanding of atmospheric physics. Because they are isolated from bright host stars, brown dwarfs are easier to study than exoplanets. Their spectra are not overwhelmed by stellar light. This allows clear observations of atmospheric features. Researchers can study molecular absorption lines. They can analyze cloud patterns. They can track chemical evolution over time. Modern telescopes have revolutionized the study of failed stars. Instruments such as JWST provide unprecedented detail. They allow observations across multiple wavelengths. They reveal subtle atmospheric structures. They detect faint thermal emissions. They open new windows into brown dwarf science. Infrared astronomy is essential for failed star research. The infrared band penetrates dust clouds. It reveals heat signatures otherwise invisible. It uncovers objects hidden in the galactic plane. It captures the glow of cool atmospheres. It records the temperature gradients within clouds. Infrared surveys have discovered many brown dwarfs near the Sun. These discoveries surprise astronomers. They suggest that our cosmic neighborhood is filled with unseen companions. These nearby objects drift quietly alongside us. Their presence adds richness to the local galaxy. They remind us that darkness often hides abundance. Failed stars also appear in star-forming regions. These regions contain turbulent gas. Fragmentation occurs at various scales. Low-mass fragments collapse into brown dwarfs. They mix with newborn stars. They form a diverse population. In these regions, failed stars experience dynamic environments. They may interact with other protostars. They may be ejected from forming clusters. Some become free-floating wanderers. Others remain in bound systems. Their early lives are more active than their later ones. The ejection of brown dwarfs is common. Close encounters between protostars can expel smaller objects, the 44 and NED. These ejected dwarfs become cosmic nomads early on. They leave their birthplace behind. They embark on solitary journeys. They drift through interstellar space without a home. This process explains why many brown dwarfs are isolated. Their isolation is not a sign of incompleteness. It is a result of dynamic beginnings. Their trajectories are shaped by gravitational interactions. Their paths are determined by chance encounters. Their destinies unfold quietly afterward. Once isolated, failed stars enter a phase of tranquility. Their environments become stable. Their internal processes slow down. Their atmospheres calm. Their cooling continues steadily. Their existence becomes a prolonged whisper. Brown dwarfs also serve as markers for stellar evolution. Their properties reveal the physics of low-mass objects. They help define the minimum mass for hydrogen fusion. They help clarify the boundary between stars and planets. Their evolution informs the broader picture of stellar populations. They fill gaps in our understanding. Failed stars are not uniform. They vary widely in age, mass, and temperature. Their atmospheres differ in composition. Their rotation rates vary. Their cloud patterns are diverse. Each one is a unique combination of cosmic parameters. This diversity is reflected in their spectra. Spectral lines shift and change with temperature. Chemical features intensify or fade. Cloud opacity varies. Infrared colors evolve. Each spectrum tells a story. Spectral classification helps organize this diversity. It provides a framework for comparing objects. It places brown dwarfs along a continuum of cooling. It highlights transitions between spectral types. It connects atmospheric chemistry with temperature. It reveals patterns hidden in complexity. The spectral sequence from M to Y is like a slow descent. It represents cooling over billions of years. It marks the gradual fade of internal heat. It shows the evolutionary pathway of failed stars. It captures the transformation from warmer embers to cold shadows. It reflects the passage of cosmic time. Failed stars carry the memory of their origins. Their mass reflects the size of their birth fragment. Their temperature reflects their age. Their composition reflects their birth environment. Their motion reflects the dynamics of their home cluster. Their existence encodes the history of star formation. Even in their dimness, they are rich with information. Their diversity reveals the complexity of stellar nurseries. Their evolution reveals the slow processes of cooling. Their atmospheres reveal chemical pathways. Their presence reveals the structure of galaxies. Their faint glow reveals the hidden architecture of the cosmos. Failed stars also hold aesthetic value. Imagining them drifting through darkness evokes calm. Their soft infrared glow suggests warmth in a cold void. Their slow evolution suggests patience. Their quiet presence suggests peace. Their endurance suggests resilience. In many ways, brown dwarfs resemble the process of falling asleep. Their cooling mirrors the slowing of thoughts. Their dimming mirrors the fading of consciousness. Their stillness mirrors the quiet of rest. Their long, tranquil existence mirrors the deepest stages of sleep. They are cosmic symbols of restfulness. As we learn more about them, we also learn more about ourselves. Their subtlety teaches mindfulness. Their calm teaches patience. Their longevity teaches humility. Their dimness teaches appreciation for quiet beauty. Their persistence teaches resilience. The study of failed stars also raises profound questions about cosmic evolution. What will the universe look like trillions of years from now? When all stars have burned out, what remains? The answer may be brown dwarfs. These quiet objects will persist long after stars fade, they will drift through a dark, expanded universe. In this distant future, the cosmos may be filled with cold brown dwarfs. Their faint warmth may be the last source of natural energy. They will be the final landmarks of structure. They will populate a universe approaching thermal equilibrium. They will embody the last remnants of starlight. They will carry the final whispers of cosmic heat. This vision is melancholic yet serene. It suggests a universe at rest, a universe without fire, a universe cooling gently into stillness, a universe where failed stars become the final custodians of warmth, a universe where silence reigns. The distant future of the universe is a place where failed stars take center stage. As time stretches on, galaxies grow dimmer. Bright stars exhaust their nuclear fuel. White dwarfs cool into black dwarfs. Neutron stars drift into colder states. Black holes slowly evaporate over unimaginable timescales. Yet, brown dwarfs continue their gentle decline. Their cooling never truly ends. They slip closer and closer to absolute zero. But they never quite reach it. Their warmth becomes a memory of gravitational collapse. Their glow becomes a whisper of ancient heat. This makes failed stars the quiet elders of the cosmos. They survive long after other objects fade. Their endurance hints at the universe's eventual destination. As everything bright diminishes, everything dim. In this twilight epoch, the faintest objects become the most lasting. The smallest embers become the final lights. Their presence in the far future represents stability. They are predictable and enduring. They do not flare violently. They do not explode. They do not collapse catastrophically. They transition slowly and peacefully. This peaceful evolution reflects their nature. They were born too small to ignite. Yet, they were born massive enough to endure. Their middle ground identity grants them longevity. Their quiet nature grants them calm. Their slow cooling grants them serenity. Astronomers sometimes call them substellar objects. This term captures their incomplete nature, but it does not capture their quiet beauty. They are more than failed stars. They are independent cosmic entities. They carve their own path through the galaxy. As substellar objects, they display fascinating physics. Their interiors are governed by quantum mechanics. Their atmospheres follow unique thermodynamic rules. Their chemistry evolves slowly but meaningfully. Their pressure and density challenge traditional models. Their behavior blends traits of planets and stars. The study of failed stars bridges scientific disciplines. It includes stellar evolution. It includes planetary science. It includes atmospheric chemistry. It includes quantum mechanics. It includes galactic dynamics. This interdisciplinary nature makes them intellectually rich. They cannot be understood through a single lens. They require collaboration between fields. They demand multiple perspectives. They embody scientific complexity. They reward comprehensive inquiry. Their internal structure is particularly intriguing. Inside, a brown dwarf, pressures are immense. Atoms are compressed tightly. Electrons resist further compression due to degeneracy pressure. This pressure supports the object against collapse. It sets brown dwarfs apart from planets. Their cores do not undergo ongoing fusion, but they are hot from their formation. This heat slowly radiates outward. As the object cools, the core temperature declines. The rate of cooling depends on mass. More massive brown dwarfs cool more slowly. The cooling curve of a brown dwarf resembles a long, gentle slope. There are no steep drops, no dramatic transitions, just a slow fade into darkness. This consistent decline mirrors the calm nature of their existence. It mirrors the slow drift of thoughts before sleep. Their cooling process reveals clues about age. By measuring temperature, astronomers can estimate how long the object has existed. This method is not perfect, but it offers valuable insight when combined with other data. Temperature-age relationships help build cosmic timelines. They help map the evolution of stellar clusters. In star-forming regions, failed stars coexist with newborn suns. They are part of the same birth population. Some are massive and bright. Others are small and dim. This diversity emerges naturally from gas cloud fragmentation. It reflects the chaotic nature of star formation. As the region evolves, failed stars drift outward. Their interactions with young stars shape their paths. Some remain bound to the cluster. Others are ejected. Their trajectories depend on local gravitational forces. Their futures are determined by early randomness. Once they leave their birthplaces, brown dwarfs embark on solitary journeys. They travel through cold, empty space. Their movements follow the gravitational pull of the galaxy. They orbit the galactic center like all stars. Their orbits are slow and elongated. Their journeys span millions of years. During their travels, they encounter various environments. They pass through interstellar clouds. They drift through empty voids. They occasionally approach stellar systems, but encounters are distant and brief. Their solitude is rarely interrupted. Their solitary existence gives them a peaceful background. They are not disturbed by stellar flares. They are not affected by supernovae unless extremely close. They live quiet, uneventful lives. Their atmospheres evolve undisturbed. Their cooling progresses smoothly. This peaceful isolation makes brown dwarfs ideal for studying long-term atmospheric changes. Unlike planets near stars, they have no external heat source. Their temperature is purely internal. This simplifies models of atmospheric chemistry. It provides clarity about the effects of cooling alone. It reveals intrinsic processes without external interference. Atmospheric models of brown dwarfs have become highly detailed. They incorporate cloud physics. They include molecular absorption lines. They simulate heat transport. They track chemical reactions over time. They attempt to reproduce observed spectra. Despite their complexity, these models are incomplete. Brown dwarf atmospheres are dynamic and strange. Unexpected features appear in observations. Cloud structures shift unpredictably. Chemical abundances vary unexpectedly. Weather patterns evolve in intricate cycles. These mysteries make brown dwarfs fascinating. They remind scientists that nature is not simple. Even dim, quiet objects contain complexity. Even failed stars hold secrets. Even cooling atmospheres host unexpected patterns. The universe never fully reveals itself. Failed stars also help calibrate evolutionary models. They are benchmarks for understanding low-mass objects. Their cooling curves act as templates. Their chemical transitions mark specific temperature regimes. Their spectra indicate atmospheric changes. Their properties guide theoretical predictions. These predictions apply not only to brown dwarfs, but also to giant exoplanets. The atmospheres of exoplanets share similarities with cooler brown dwarfs. Cloud formation processes overlap. Chemical compositions align at certain temperatures. Heat transport mechanisms resemble each other. Thus, brown dwarf research benefits planetary science. By studying failed stars, scientists refine techniques for studying exoplanets. Spectroscopic methods improve. Atmospheric models expand. Cloud simulations become more accurate. Molecular line databases grow. Observational strategies evolve. In this way, brown dwarfs are stepping stones. They lead to deeper understanding of exoplanetary atmospheres. They prepare scientists for exploring distant worlds. They provide a natural laboratory. They offer glimpses of exotic environments. They stimulate curiosity about life elsewhere. Even without fusion, failed stars exhibit internal structure. Their cores are not empty. They contain dense materials. Temperatures remain high for millions of years. This heat gradually diffuses outward. It fuels long-term atmospheric changes. The outer layers of brown dwarfs cool faster. This creates temperature gradients. These gradients drive atmospheric circulation. They produce slow, sweeping winds. They encourage rotating cloud bands. They generate deep, layered weather. Weather on failed stars differs from weather on planets. There is no solid surface. Atmospheric layers transition gradually into the interior. Pressure rises steadily with depth. Temperature increases smoothly. Clouds form at specific pressure levels. Silicate clouds appear at high temperatures. Iron droplets may rain down. Alkali metals contribute to spectral features. At lower temperatures, methane dominates absorption. At even colder temperatures, ammonia becomes significant. Each stage marks a new chapter in atmospheric evolution. This evolution is slow but continuous. It mirrors the gentle passage of time. It resembles long, unbroken cycles. There are no abrupt changes. There are no violent transitions. Only steady, dreamlike cooling. The calmness of this cooling process parallels deep relaxation. As the object loses heat, its glow softens. Its storms weaken. Its clouds thin. Its gravity remains constant, but its atmosphere quiets. Its existence becomes more peaceful. The serenity of brown dwarfs makes them ideal metaphors for rest. They teach us that quietness can be enduring. They show that fading does not mean vanishing. They illustrate that calm can be powerful. They remind us that the universe holds many forms of softness. They whisper that stillness is natural. Failed stars also inspire poetic imagery. They drift like forgotten embers. They glow like distant memories. They cool like settling thoughts at night. They wander like gentle shadows. They persist like patient breaths in sleep. The idea of countless failed stars surrounding us evokes comfort. We are not alone in brightness. We are surrounded by quiet companions. Their presence is subtle but vast. Their population is immense. Their influence is gentle but pervasive. They form an invisible halo around the Milky Way. They populate the galaxy's thin disk. They inhabit star clusters as hidden members. They drift between bright stars as dark wanderers. They contribute mass without illumination. They support gravitational balance without shine. Their hidden role mirrors many quiet forces in life. Some influences are not visible. Some strengths are not loud. Some contributions are not obvious. Yet they matter deeply. Their importance grows with understanding. Failed stars teach patience in discovery. They cannot be seen easily. They resist quick detection. They hide in infrared silence. They require careful study. They reveal themselves gently. This gentleness makes them soothing subjects. Their dimness calms the mind. Their slow evolution slows the breath. Their drifting evokes quiet movement. Their cooling reflects deep rest. Their persistence encourages peace. The universe contains many types of objects. Some burn with intensity. Some explode with violence. Some collapse dramatically. But failed stars do none of these things. They simply persist. Their persistence is not grand or dramatic. It is subtle and enduring. It is soft and patient. It is slow. Yet, it lasts longer than almost anything else. It survives cosmic cycles. Because of this, failed stars are often compared to cosmic sleepers. They lie in a state of perpetual slumber. Their heat fades like a long exhale. Their glow dims like closing eyes. Their storms quiet like settling thoughts. Their existence becomes a long, peaceful dream. This dreamlike quality resonates with human imagination. It invites stillness. It encourages relaxation. It fosters introspection. It mirrors the journey into sleep. It aligns with the gentle fall into dreaming. Even their names evoke softness. Brown dwarf suggests warmth and earthiness. White dwarf suggests calm and quiet. Failed star suggests humility and gentleness. These names connect science with emotion. They reflect the poetic nature of cosmic objects. As failed stars continue cooling, their glow weakens. Their light becomes undetectable with current instruments. But they never vanish completely. Their mass remains. Their gravity persists. Their presence continues. This persistence mirrors the quiet endurance of thoughts before sleep. Even as consciousness fades, awareness remains. Even as light dims, existence continues. Even as intensity lessens, presence endures. Failed stars embody this continuity. They reflect the gentle path between wakefulness and rest. Their future is long and unhurried. Their journey is calm and steady. Their glow fades but does not collapse. Their warmth diminishes but does not disappear entirely. Their presence remains woven into the galaxy. Their influence persists through cosmic time. Even in their dimmest stages, failed stars remain active in subtle ways. Their atmospheres, though cool, continue to evolve. Chemical reactions proceed slowly in the cold. Molecules bond and separate in rhythmic patterns. Clouds form and dissipate. Drifting cycles. Their atmospheric layers breathe with temperature shifts. These shifts occur over decades, centuries, or longer. They are imperceptible on human timescales. But over cosmic time, they create profound changes. Cloud bands shift across the surface. Storm systems migrate and fade. Pressure zones reorganize gently. This slow atmospheric evolution mirrors the gradual quieting of a resting mind. Thoughts drift in and out. Long, slow waves of awareness move gently. Nothing is abrupt. Nothing is sudden. Everything softens into a tranquil flow. Failed stars display different weather at different temperatures. Warm brown dwarfs host silicate and iron clouds. These clouds form at high altitudes. They swirl like mineral dust storms. They glow faintly in infrared light. They shape the object's early atmosphere. As the dwarf cools, these mineral clouds sink. They rain downward into hotter layers. The upper atmosphere becomes cleaner. Methane and water vapor dominate. The clouds become darker and patchier. Shadows replace brightness. In even colder dwarfs, cloud layers almost disappear. Only thin wisps remain. Ammonia begins to influence the spectrum. Infrared colors shift to cooler tones. The brown dwarf enters its quietest stage. Its atmospheric patterns become minimal and serene. This progression from cloudiness to clarity is peaceful. It resembles fog lifting over a calm landscape. The world becomes simpler. The skies become quieter. The atmosphere becomes still. The object settles into deeper tranquility. Studying these atmospheric changes gives scientists insights into temperature transitions. Each molecular signature represents a milestone. Each cloud feature marks a point along the cooling curve. These milestones help calibrate models of substellar evolution. They link chemistry with physics. They connect observation with theory. Because failed stars cool slowly, they offer long-term stability. This stability is ideal for certain types of observations. Scientists can track changes without rapid fluctuations. They can study chemical processes that unfold gradually. They can observe weather cycles that last for months or years. They can refine their understanding of low-temperature atmospheres. One of the most intriguing aspects of brown dwarfs is their brightness variability. Even though they are faint, their light shifts subtly. Right one. These shifts occur as cloud structures rotate in and out of view. It is a soft pulsing of warmth, a gentle modulation of glow, a slow cosmic rhythm. This pulsing can be measured with precision instruments. It reveals the rotation period of the dwarf. It maps atmospheric features. It tracks the evolution of cloud layers. It uncovers hidden motion within the object. It adds depth to our understanding of their weather. Some brown dwarfs show strong brightness changes. These changes hint at large storm systems. Storms may span great swaths of the surface. They rise and fall over long timescales. They shift like slow-moving waves. They create rhythmic patterns in infrared emissions. Other dwarfs show minimal variability. Their atmospheres are calm and uniform. They rotate smoothly with almost no changes in brightness. These objects represent the quietest stage of atmospheric evolution. Their clouds are thin or absent. Their chemical layers remain stable. This difference between active and quiet dwarfs forms a spectrum of behavior. It illustrates how diverse failed stars can be. Some are full of slow, drifting storms. Some are smooth and nearly featureless. Some transition between states over time. Each one has its own atmospheric personality. The existence of weather on failed stars may seem strange. After all, they do not have sunlight to drive atmospheric circulation, but their internal heat is sufficient. This heat rises through the atmosphere. It creates convection cells. It drives winds and cloud movement. These wind patterns are slow compared to those of planets. They are governed by thermal gradients rather than external radiation. Cloud particles drift gently in these currents. Storms rotate under the influence of rapid spin. Chemical species mix and separate. The atmosphere becomes a complex, layered system. Infrared observations reveal these patterns. Different wavelengths probe different altitudes. Scientists use them to reconstruct vertical structures. These structures show where clouds form. They show where molecules concentrate. They show how heat flows through the atmosphere. Failed stars are like laboratories suspended in space. Their isolation provides clarity. Their cooling provides a timeline. Their atmospheres provide diversity. Their spectra provide insight. Their evolution provides scientific continuity. Their characteristics also challenge our sense of scale. They are massive, yet quiet. They are dense, yet gentle. They are hot inside, yet cold outside. They are dark, yet full of detail. They are distant, yet scientifically intimate. Brown dwarfs exist in a liminal space. They are not fully planets. They are not fully stars. They occupy the boundary between categories. This boundary is fertile ground for discovery. It reveals the fluidity of cosmic classification. Nature does not follow human labels. It creates objects of every mass and temperature. It blends characteristics freely. It shapes diversity through physics, not language. Failed stars illustrate this truth. They defy simple definitions. Their hybrid nature enriches astrophysics. It demonstrates the continuity between planets and stars. It fills the gap between giant planets and low-mass stars. It completes the spectrum of celestial bodies. It links stellar formation with planetary processes. It unites separate fields under one phenomenon. Studying failed stars also expands our understanding of extreme environments. Their atmospheres operate under high pressures. Their chemistry forms at unusual temperatures. Their weather systems mix exotic materials. Their clouds consist of minerals rather than water. Their storms involve substances that condense at thousands of degrees. This exotic nature challenges existing theories. It forces scientists to create new models. It encourages new approaches to atmospheric physics. It refines techniques for analyzing complex spectra. It inspires more precise simulations. It pushes the boundaries of knowledge. Instruments like the James Webb Space Telescope deepen this exploration. JWST can detect faint signatures from cool atmospheres. It can resolve chemical lines with exceptional sensitivity. It can observe tiny variations in brightness. It can map cloud layers in unprecedented detail. It opens new dimensions of failed star research. These capabilities reveal complexity in the dimmest objects. They uncover patchy clouds on cool dwarfs. They trace slow chemical evolution. They detect subtle heat flows. They expose hidden atmospheric structures. they transform our understanding of substellar objects. As technology improves, more failed stars will be discovered. Infrared surveys will identify cooler and fainter dwarfs. Longer observations will find subtle variability. Larger telescopes will resolve finer details. Better models will decode complex spectra. Research will evolve as steadily as the objects themselves. Each discovery adds depth to our cosmic perspective. It expands our understanding of star formation. It reveals new atmospheric phenomena. It challenges preconceived notions. It enriches astrophysics with nuance. It emphasizes the importance of subtlety. Failed stars also highlight the role of gravity in shaping the universe. Their formation relies on gravitational collapse. Their structure is defined by gravitational pressure. Their evolution is driven by heat generated through contraction. Their cooling reflects the gradual release of gravitational energy. They are pure expressions of gravity's gentle power. Gentle power. Gravity shapes their birth. Gravity shapes their existence. Gravity shapes their long-term fate. Gravity binds them to galactic orbits. Gravity influences their interactions with other objects. Gravity ensures their persistence across cosmic time. Their quiet nature is a reminder that gravity can be subtle. Not all gravitational effects are dramatic. Some are slow and steady. Some unfold over billions of years. Some manifest as gentle cooling. Some appear as faint infrared glows. This subtle, gravity-driven evolution makes failed stars cosmic beacons of patience. They change slowly. They endure the passage of time. They reflect the long rhythms of the universe. They embody deep time in a way few objects can. They inspire contemplation. Contemplating failed stars invites introspection. It draws attention to the value of slowness. It highlights the beauty of dim light. It elevates the quiet over the loud. It honors persistence over brilliance. It celebrates softness over spectacle. In many ways, brown dwarfs provide a cosmic metaphor for inner calm. They remain stable through long stretches of time. They do not burn intensely. They do not flare unpredictably. They simply exist peacefully. They drift gently through the galaxy. This gentle drift mirrors the feeling of drifting into sleep. Thoughts float like clouds in a cooling atmosphere. Awareness softens like fading infrared light. Breathing settles like slow rotational rhythms. Consciousness dims like the quiet glow of a Y dwarf. Peace spreads like cooling layers in a substellar sky. Failed stars embody the essence of cosmic serenity. They are the universe's softest lights. They are the galaxy's quietest companions. They are the night's most peaceful wanderers. They are the shadows that shape the structure of space. They are the embers that never ignited. Their existence reminds us that not everything must shine to be meaningful. Sometimes, the most enduring things glow softly. Sometimes, the most powerful forces act quietly. Sometimes, the most important contributions are unseen. Sometimes, the deepest beauty lies in shadow. Sometimes, the universe speaks in whispers. Failed stars are often overlooked because of their faintness. Yet their subtle presence reveals much about the galaxy. They populate regions that appear empty. They contribute mass to gravitational structures. They form bridges between planetary and stellar populations. They illuminate the transition between light and darkness. Their faint glow carries information about their internal states. Even the weakest infrared signal tells a story. The temperature reveals age. The spectrum reveals chemistry. The variability reveals weather. Everything they emit is a quiet announcement of their nature. Because of their dimness, failed stars require creative methods to detect. Astronomers use parallax measurements to find nearby dwarfs. They track proper motion across the sky. They analyze infrared colors in wide surveys. They search for gravitational effects on companion stars. They use machine learning to sift through vast data sets. These techniques reveal patterns hidden in darkness. They uncover faint sources among millions of brighter ones. They identify objects that would otherwise remain invisible. They show that the universe holds far more than meets the eye. They remind us that perception is limited by tools. They highlight the value of improved technology. Brown dwarfs, once purely theoretical, have become central to modern astrophysics. Their discovery changed the understanding of star formation. Their existence filled a gap in the mass distribution of celestial objects. Their study opened new research pathways. Their diversity expanded models of atmospheres. Their faintness challenged observational methods. Now they serve as reference points for future discoveries. They help calibrate instruments designed for exoplanet research. They reveal what low-temperature atmospheres look like. They show how clouds behave in exotic conditions. They guide the classification of newly found objects. They provide context for planetary formation. Some failed stars exist in binary systems, with true stars. In such systems, they orbit like massive companions. Their gravitational influence can slightly shift the star's motion. This shift produces measurable wobbles. These wobbles expose the presence of the unseen dwarf. They turn subtle gravitational signatures into scientific clues. These systems also offer opportunities to study interactions. The star illuminates the brown dwarf faintly. Its light reveals reflective properties. Its radiation influences atmospheric chemistry. It highlights cloud layers more clearly. It enhances the contrast between different atmospheric depths. Brown dwarfs in multiple systems reveal gravitational hierarchies. Some systems include 3 or more objects. Orbital resonances develop between them. Their synchronized motions create stable configurations. These resonances act like cosmic choreography. They demonstrate the elegance of gravitational balance. Systems containing both stars and failed stars are especially revealing. They allow direct comparisons of luminosity. They show how temperature scales with mass. They highlight the boundary of nuclear ignition. They capture the difference between star and not star. They emphasize the continuum of cosmic formation. Failed stars also exist in clusters. In these environments, they interact with many neighbors. Close encounters alter their trajectories. Ejections occur frequently. Some end up as solitary wanderers. Others remain bound to the cluster for billions of years. Clusters reveal population statistics. They show how many failed stars form relative to true stars. They help calibrate theoretical models. They demonstrate the natural distribution of masses. They show that brown dwarfs form commonly. They confirm that substellar formation is a normal outcome. Failed stars also appear in ancient star clusters. These clusters are billions of years old. Their brown dwarfs have cooled significantly. They sit near the bottom of the cluster's brightness distribution. Detecting them requires deep infrared imaging. Their presence reflects the cluster's formation history. In old clusters, failed stars serve as cosmic clocks. Their cooling traces the passage of enormous timescales. Their temperatures correspond to specific ages. Their faintness reveals the elapsed time since formation. They help refine the ages of stellar populations. They serve as markers of galactic evolution. The coldest brown dwarfs blur the line between stars and planets completely. Their temperatures resemble those of Jupiter and Saturn. Their atmospheres contain similar molecular signatures. They may host cloud patterns reminiscent of gas giants. Their internal processes mirror planetary physics. They represent the most planet-like stage of failed star evolution. Despite their planet-like characteristics, they are not planets. They formed from direct collapse, not from accretion disks. They lack a solid core. Their mass far exceeds typical planetary masses. Their composition is more star-like. Their structure follows stellar principles. This dual identity highlights the continuum of cosmic objects. Nature creates gradients, not categories. Mass determines internal processes. Temperature determines atmospheric behavior. Formation history determines classification. But the boundaries between groups remain flexible. Even the term failed star can be misleading. It implies an expectation of ignition. But nature has no such expectation. Brown dwarfs simply represent one outcome of formation. They are not failed, just different. They follow a distinct evolutionary path. Their path is quieter and slower than that of stars. They do not experience the tumult of fusion. They do not produce intense radiation. They do not generate solar winds. They evolve in peace. They exist in a state of gentle decline. This quiet decline contributes to their appeal. They embody cosmic restfulness. They demonstrate that grand events are not required for significance. They reveal that stillness holds meaning. They show that subtlety is powerful. They remind us that quiet forces shape the universe. Failed stars also raise questions about habitability. Could life arise on planets orbiting them? The lack of strong visible light is a challenge. But life may adapt to infrared radiation. Thermal gradients could drive biological processes. Exotic photosynthesis might evolve. Such speculation motivates astrobiology. It expands the search for life. It challenges assumptions about habitability. It opens doors to new models of ecosystems. It encourages researchers to explore non-traditional environments. It broadens humanity's vision of possible life. If life existed near a failed star, it would live in perpetual twilight. Its world would glow in shades of infrared. Its sky would lack bright daylight. Its surface would cool slowly over time. Its ecosystems would depend on faint heat. Its evolution would unfold in dim serenity. Failed stars could also support subsurface oceans on orbiting moons. Tidal heating could provide additional energy. Combined with faint infrared warmth, it might sustain liquid water. This possibility resembles moons in our own solar system. Europa and Enceladus demonstrate such potential. The same principles could apply near brown dwarfs. Thus, failed stars expand the search for habitable worlds. They enlarge the boundary of life-friendly environments. They challenge assumptions about light and heat. They show that even dim objects might host complex systems. They encourage openness to surprising possibilities. They make the universe feel more abundant. Studying failed stars also informs the search for rogue planets. Some planetary mass objects may drift freely through space. They resemble small brown dwarfs in temperature and composition. Finding one requires understanding how failed stars behave. Atmospheric models overlap between the two. Spectral signatures align in key regions. Rogue planets and failed stars share the darkness. They roam without parent stars. They drift through the galaxy alone. Their glows are minimal. Their atmospheres are cold. Their presence is subtle. By comparing the two, astronomers refine detection techniques. They classify free-floating objects more accurately. They distinguish low-mass brown dwarfs from rogue planets. They read the faint patterns in infrared spectra. They decipher clues from temperature gradients. They interpret signals from chemical lines. Failed stars also reveal the efficiency of star formation. Not all collapsing gas becomes a star. Some becomes a giant planet. Some becomes a brown dwarf. Some remains in diffuse clouds. This variety reflects the complexity of formation environments. Understanding these outcomes requires studying failed stars carefully. Their masses provide lower bounds. Their formation frequency reveals fragmentation behavior. Their distribution maps the efficiency of collapse. Their population helps refine theoretical models. Their variety reflects the richness of cosmic processes. As researchers analyze more brown dwarfs, patterns emerge. Mass distribution follows predictable curves. Atmospheric chemistry correlates with temperature. Brightness variability aligns with rotation. Cloud structures depend on pressure levels. Cooling rates match theoretical predictions. Yet mysteries remain. Some brown dwarfs behave unexpectedly. Their variability is stronger than models suggest. Their atmospheric layers show unusual features. Their chemical abundances challenge predictions. Their spectra reveal unanticipated absorption lines. These anomalies push science forward. They force researchers to revise theories. They encourage the creation of new models. They drive innovation in observational methods. They deepen our understanding of physics. They expand the boundaries of what is known. One of the most profound questions is how cold a failed star can become. Over trillions of years, they approach absolute zero. Yet they never quite reach it. Their internal heat fades asymptotically. Their cooling slows dramatically. Their temperature becomes a near constant whisper. This asymptotic cooling reflects thermodynamic principles. Heat transfer becomes less efficient as temperature drops. The gradient with space decreases. Energy radiates more slowly. Cooling becomes a matter of eternity. Failed stars become cosmic timekeepers. Their endurance surpasses most cosmic structures. Stars live for billions of years. Brown dwarfs survive for trillions. They remain while galaxies evolve. They persist through cosmic transformations. They outlast the age of starlight. In the deep future, they will be among the final active objects. Their faint heat will stand out in a cold universe. Their persistence will seem extraordinary. They will glow softly in an expanding, cooling cosmos. They will anchor the last warm structures. They will embody the remnants of stellar birth. Imagining this future inspires both awe and calm. The universe becomes a quiet, dim place. Motion slows. Light fades. Energy disperses. Only the softest glows remain. Failed stars become symbols of cosmic endurance. They stand as reminders that quiet things last. They embody resilience through subtlety. They represent longevity through stillness. They show that softness can outlast brilliance. They teach that enduring light does not need to shine brightly. Their existence invites a tranquil mindset. Thinking about them slows the breath. It encourages long, gentle reflection. It mirrors the peace of a dark, quiet night. It soothes the imagination. It lulls the mind toward rest. Failed stars possess a quiet magnetism that draws scientific curiosity. Their faint glow hides deep complexity. Their cool atmospheres conceal rich chemistry. Their slow evolution invites careful study. Their subtle variability offers delicate clues. Their existence reflects the hidden diversity of the cosmos. Magnetic fields in brown dwarfs provide an especially intriguing window into their interiors. Most brown dwarfs generate magnetic fields through internal convection. Hot material rises and cool material sinks. This motion creates currents. The currents generate magnetic forces. These fields extend far into the surrounding space. Despite their faintness, failed stars can produce strong radio emissions. These emissions arise from electrons spiraling along magnetic lines. They create bursts of radio energy. These bursts can be detected with radio telescopes. They reveal the intensity of the magnetic field. They show that brown dwarfs are not entirely quiet. Some brown dwarfs experience magnetic storms. These storms are weaker than those on stars, but they produce measurable flares at radio wavelengths. They indicate internal dynamism. They suggest layers of complex electrical activity. They reveal hidden energetic processes. The magnetism of brown dwarfs changes with age. Young dwarfs rotate quickly and generate stronger fields. Old dwarfs rotate more slowly. Their magnetic fields weaken. Their radio emissions fade. Their activity diminishes gently over time. This magnetic evolution parallels thermal evolution. As heat declines, dynamo processes slow. Convection becomes less vigorous. Electrical currents weaken. Magnetic fields soften. The object enters a quieter state. Scientists use magnetic activity to probe internal structure. Radio pulsations reveal rotation periods. Magnetic strength indicates conductivity. Magnetospheric emissions map the object's architecture. Magnetic features expose unseen layers. They provide clues about hidden physics. The magnetism of failed stars resembles that of giant planets. Jupiter emits strong radio waves. Brown dwarfs show similar behavior at higher intensities. This similarity connects planetary physics with substellar physics. It bridges the study of magnetic dynamos across mass ranges. It highlights the unity of physical processes in nature. The auroras of brown dwarfs are an especially beautiful phenomenon. Just like planets, brown dwarfs can host auroral displays. Charged particles interact with magnetic fields. These particles emit light in specific wavelengths. on brown dwarfs. Auroras glow primarily in infrared and radio. They produce delicate pulses across the spectrum. Because brown dwarfs lack strong stellar winds, their auroras behave differently. They may rely on interactions with unseen companions. They may be powered by internal processes alone. Their mechanisms remain partly mysterious. Their emissions hint at unseen interactions. Their patterns inspire further investigation. Some brown dwarfs have companions that behave like moons. The companion interacts with the magnetic field. This interaction produces auroral currents. These currents create periodic radio emissions. They resemble the Jupiter Io system. They reveal the presence of unseen bodies. Detecting such emissions helps find companions. It opens a new method of identifying exoplanets. It reveals mass and orbital characteristics. It uncovers hidden relationships between objects. It demonstrates the sensitivity of magnetic observations. It expands detection techniques beyond visible light. The cool temperatures of brown dwarfs influence their magnetic chemistry. In warm dwarfs, ionized particles travel easily. In cool dwarfs, ionization drops. Conductivity changes. Magnetic coupling becomes weaker. Auroral energy moves through different channels. These changes create distinct signatures in different temperature regimes. They help classify dwarfs with greater precision. They reveal how magnetic behavior evolves. They connect temperature with atmospheric charge. They unify magnetic and thermal models. They link external emissions with internal processes. Magnetic fields also affect atmospheric dynamics. They shape storm patterns. They influence cloud rotation. They alter the distribution of charged molecules. They enhance or suppress certain wind currents. They quietly sculpt atmospheric behavior. Failed stars are deeply influenced by rotation. Rapid rotation enhances atmospheric mixing. It generates centrifugal forces. It shapes cloud bands into elongated structures. It accelerates magnetic dynamos. It intensifies weather cycles. Some brown dwarfs rotate in only a few hours. These speeds approach rotational limits. The objects bulge slightly at the equator. Their shapes become subtly oblate. Their weather bands stretch across wide latitudes. Their clouds curve into sweeping arcs. These rotational effects resemble those on giant planets. Jupiter and Saturn show banded patterns. Failed stars exhibit similar structures, but their clouds involve exotic materials. They contain silicate grains instead of water droplets. They form mineral storms rather than vapor storms. Such storms evolve slowly. Silicate crystals condense at high altitudes. They drift downward under gravity. They evaporate in hotter layers. The cycle repeats continuously. This produces a mineral-based weather system. Iron droplets can also form in hot dwarfs. These droplets condense like metallic rain. They fall into deeper layers where temperatures rise. They vaporize and re-enter circulation. This iron cycle affects infrared emission. It modulates brightness in subtle patterns. The idea of iron rain is both exotic and soothing. It suggests a surreal environment where metal behaves like water. It evokes images of shimmering droplets falling in slow motion. It creates a dreamlike atmosphere of quiet storms. It highlights the strangeness of exotic worlds. It adds depth to the cosmic story of failed stars. Brown dwarfs are categorized by spectral type. The sequence from M to Y represents cooling stages. Each stage marks a shift in chemistry. Each shift produces new atmospheric features. Each feature modifies the infrared glow. Each glow reveals a different chapter in evolution. M-type brown dwarfs are closest to true stars. They show hints of metal oxides. Their atmospheres are warm and active. Their spectra contain strong molecular bands. Their clouds are thick. Their storms are dynamic. L-type dwarfs are cooler and dusty. Silicate clouds dominate their appearance. Infrared colors shift toward the red. Brightness variability becomes more pronounced. Weather patterns intensify. Cloud layers grow complex. Type dwarfs are even cooler. Methane absorption appears prominently. Silicate clouds sink beneath visible layers. Infrared colors transition to blue. Brightness variations become smoother. Atmospheres become clearer and calmer. Y-type dwarfs are the coldest of all. Their temperatures resemble those of hot rooms. Ammonia signatures appear in their spectra. Their clouds are faint or absent. Their glow is delicate and whisper-like. Their atmospheres exist near the edge of star-like behavior. This progression forms a beautiful narrative. It is a slow descent through cosmic temperatures. It is a journey from heat to cold. It is a movement from complexity to simplicity. It is a transformation from cloudiness to clarity. It is the natural arc of a failed star's life. The boundaries between these types are fluid. Objects may transition across categories. Their classification depends on temperature, not age alone. Two dwarfs of the same age may be different types. Two dwarfs of the same type may be different ages. Their diversity reflects their formation histories. Their motion through space reveals additional details. Failed stars orbit the galactic center like all other objects. Their orbits vary widely. Some follow circular paths. Others drift in elongated ellipses. A few plunge above and below the galactic plane. These orbital motions preserve ancient stories. They reflect the environment where the dwarf was born. They retain the momentum of their cluster origins. They encode the gravitational influences of early interactions. They reveal the distribution of mass in the galaxy. They help map the Milky Way's gravitational potential. The local neighborhood of the Sun contains many failed stars. Some lie only a few light years away. Their faintness hid them for centuries. Infrared surveys revealed their presence. They drift quietly among brighter stars. They accompany the Sun in its galactic orbit. Their proximity adds beauty to the night sky. Although invisible, they are present. They surround us like calm guardians. They drift in silence near our solar system. Their hidden presence enriches the cosmic neighborhood. Their subtle gravity tugs faintly on the galactic tapestry. Even though they do not shine, failed stars impact star formation. Their gravity influences nearby gas clouds. Their presence affects fragmentation. Their interactions can prevent collapse. Their mass helps regulate cluster density. Their existence adds nuance to stellar nurseries. Brown dwarfs also play a role in binary evolution. If paired with a star, they can affect mass transfer. They can stabilize or destabilize orbits. They can alter tidal interactions. they can prevent certain evolutionary pathways. Their gravitational influence is quiet but persistent. Failed stars occasionally form in pairs. Binary brown dwarf systems orbit each other gracefully. Their mutual gravity creates elegant patterns. Their orbits reveal their masses. Their interactions reveal their density. Their evolution reveals substellar dynamics. Some systems include nearly identical twins. Their similar temperatures suggest shared origins. Their parallel cooling tells a synchronized story. Their atmospheres evolve similarly. Their brightness variations mirror one another. Their companionship adds poetic symmetry. Other pairs differ significantly. One may be warmer. One may be cooler. Their divergence reveals the sensitivity of cooling to mass. It highlights subtle differences in formation. It tells a more complex story of evolutionary pathways. The existence of brown dwarf binaries challenges theories. It questions how such low-mass objects remain bound. It suggests specific formation mechanisms. It provides constraints for fragmentation models. It improves simulations of cloud collapse. It enriches the understanding of binary creation. The calmness of failed stars extends into their binary relationships. Their orbits evolve slowly. Their interactions remain stable. Their motion is predictable. Their companionship persists over billions of years. Their dance through space is a slow, graceful waltz. This waltz reflects the serenity of their nature. Nothing in their lives is rushed. Nothing unfolds abruptly. Everything transitions smoothly. Their existence is a lesson in cosmic patience. Their evolution is a demonstration of gradualism. The more scientists study failed stars, the more they appreciate their quiet beauty. They are not dramatic. They are not explosive. They do not illuminate galaxies, but they persist quietly. They endure gracefully. Their endurance itself becomes a source of fascination. It represents stability in a dynamic universe. It symbolizes resilience through subtlety. It embodies the longevity of low-energy processes. It reflects the persistence of faint heat. It captures the poetry of cosmic stillness. Failed stars remind us that the universe holds many rhythms. Some objects flicker with intensity. Some burn with violent passion. Some collapse with sudden force. But failed stars move to a slower rhythm. A rhythm as soft as steady breathing. This rhythm resonates with the human desire for rest. It invites the mind to slow down. It encourages the body to soften. It soothes the senses. It instills peace. It guides consciousness toward sleep. Failed stars drift through the galaxy as gentle participants in a vast cosmic ballet. Their movements follow gravitational currents shaped by billions of stars. They complete slow orbits around the galactic center. Their paths stretch across hundreds of thousands of light years. They weave through spiral arms like silent travelers. Their presence adds depth to the galaxy's unseen structure. These drifting paths are determined by ancient histories. Each failed star carries the momentum of its birth environment. Some were formed in crowded nurseries. Others emerged in calmer, isolated regions. Their early interactions shaped their trajectories. Their journeys reflect the chaos of star formation. Brown dwarfs experience few collisions. Space is vast and mostly empty. Close encounters rarely occur. Their solitude remains undisturbed. their atmospheres evolve without disruption. Their cooling continues uninterrupted across eons. This uninterrupted evolution is scientifically valuable. It allows researchers to track slow atmospheric processes. It provides insight into low-temperature chemistry. It gives clear examples of long-term thermal decline. It helps refine cooling models. It reveals the effects of time on substellar objects. The silence surrounding failed stars is profound. They produce little light. They emit no significant radiation. They generate slow, gentle winds. They drift without disturbing nearby objects. They blend into the cosmic darkness. In this silence lies tranquility. It mirrors the stillness of a calm night. It resembles the quiet moments before sleep. It evokes the deep softness of rest. It radiates a muted serenity. It resonates with peaceful introspection. Imagining a failed star evokes imagery of quiet landscapes. A dim ember floating in the void. A soft glow lingering in endless darkness. A warm memory fading into stillness. A hidden light drifting through space. A solitary wanderer surrounded by stars. The combination of heat and darkness creates a gentle contrast. This story, contrast, it is neither cold nor bright. It occupies a middle state. This middle state feels balanced. It symbolizes equilibrium. It reflects the harmony of cosmic forces. Failed stars embody the concept of equilibrium. Gravity pulls inward. Degeneracy pressure pushes outward. The two forces balance perfectly. This balance replaces the fusion-powered equilibrium of true stars. It sustains the object for trillions of years. This equilibrium remains stable as the object cools. Its diameter barely changes. Its mass remains constant. Its structure resists collapse. Its atmospheric layers reorganize calmly. Its evolution continues smoothly. The structural stability of brown dwarfs reveals the beauty of physics. Quantum mechanics supports them. Thermodynamics guides their cooling. Chemistry shapes their atmospheres. Gravity defines their form. All forces work in quiet harmony. This harmony represents a cosmic lullaby. It is soft and persistent. It unfolds slowly. It eases the mind. It removes urgency. It invites rest. Failed stars also remind us that cosmic beauty exists at every scale. Not only in supernovae or galaxies, not only in blazing stars, but in dim, humble objects, in quiet, faint lights, in subtle expressions of physics. Their subtlety encourages contemplation. It shifts focus from spectacle to simplicity. It highlights the elegance of low-energy systems. It underscores the value of slow processes. It reveals the importance of patience in discovery. It celebrates the quiet corners of the universe. These quiet corners hold stories just as rich as bright ones. Stories of slow formation. Stories of gentle drift. Stories of unhurried change. Stories of perseverance. Stories of hidden influence. Failed stars influence their surroundings without drawing attention. Their gravity shapes the distribution of matter. Their mass affects the orbits of neighbors. Their presence alters star cluster dynamics. Their cooling contributes to infrared backgrounds. Their rarity at extreme temperatures defines population limits. Even though their contributions are subtle, they are essential. They act as quiet anchors in the cosmic tapestry. They help maintain galactic equilibrium. They absorb some of the chaos of formation. They regulate the fragmentation of gas clouds. They fill the galaxy with diversity. Diversity is one of the universe's greatest themes. Every mass range produces a unique outcome. Every temperature range hosts different chemistry. Every density regime defines new behavior. Brown dwarfs represent a unique combination. They occupy a rare but natural niche. This niche is defined by limits. The limit of mass needed for fusion. The limit of cooling due to degeneracy, pressure. The limit of brightness detectable by telescopes. The limit between light and darkness. The limit between planet and star. Failed stars rest on that limit gracefully. They never cross into full starlight. They never collapse into planetary status. They hover in between. They persist in the in-between space. They embody cosmic liminality. Liminality makes them fascinating. They show that boundaries can be rich with meaning. They illustrate that transitions matter. They highlight the beauty of intermediate states. They demonstrate that not everything must fit neatly into categories. They celebrate the complexity of nature's continuum. Their internal structure deepens this interest. Below the atmosphere lies a sea of gas. Pressure increases with depth. Molecules compress into dense layers. Atoms crowd closer and closer together. Electrons resist further compression. This resistance produces electron degeneracy pressure. It supports the object against collapse. It replaces the need for fusion. It defines the star's radius. It limits the effects of increasing mass. It creates a firm, unchanging interior. This interior behaves like a superheated fluid. There is no solid surface. There are no distinct boundaries. Layers transition smoothly. Heat moves through convection and conduction. Currents circulate slowly through the deep interior. The smoothness of these transitions adds to the star's serenity. There are no abrupt shifts. There are no violent boundary layers. There are no sudden structural changes. Everything flows gently. Everything evolves with quiet continuity. Even the energy within a failed star moves peacefully. It diffuses outward through calm gradients. It radiates softly into space. It diminishes with delicate consistency. It cools like a dimming ember. It fades like a quiet memory. This fading is not a sign of loss. It is a natural process. It reflects the universe's gradual march toward equilibrium. It shows the elegance of thermal decline. It demonstrates the beauty of slow processes. It affirms that nothing lasts forever, yet nothing ends abruptly. Failed stars persist far beyond the lifespan of typical stars. Their endurance represents cosmic longevity. They outlive the brightest suns. They persist after galaxies transform. They survive the death of nearby stars. They remain while cosmic structures evolve. In the far future, they will be among the last warm objects in the universe. Their faint infrared glow will linger. Their internal heat will persist. Their atmospheres will shift slowly toward the coldest chemistry. Their radiance will soften almost to invisibility. Yet, they will endure. Imagining a universe filled only with failed stars is deeply peaceful. No explosions disturb the silence. No bright light breaks the darkness. No stellar winds sweep across space. Only faint warmth floats in the void. Only gentle glows whisper through darkness. This future universe resembles a cosmic night. It is quiet and timeless. It lacks turmoil. It lacks intensity. It becomes a resting place for matter. It becomes the ultimate realm of peace. The presence of failed stars in such a universe becomes symbolic. They represent the last sparks of creation. They carry the final warmth of collapsing gas clouds. They embody the memory of starlight. They preserve the last traces of birth. They keep the universe from total silence. Their faint glow becomes a metaphor for persistence, a metaphor for gentle endurance, a metaphor for soft resilience, a metaphor for quiet strength, a metaphor for the beauty of subtle light. Failed stars encourage us to value subtlety in our own lives. Not every contribution must be bright. Not every impact must be loud. Not every success must be dazzling. Some of the most meaningful things glow quietly. Some of the most enduring things shine softly. This perspective invites calm reflection. It helps dissolve the pressure for intensity. It shifts focus to longevity. It shifts attention to resilience. It celebrates peaceful existence. It honors the quiet journey of becoming. Failed stars are reminders that the universe contains infinite forms of softness. Soft light, soft heat, soft movement, soft gravity, soft evolution. And all these forms of softness offer comfort. They invite the mind to rest. They soothe the senses. They ease the weight of thought. They create a tranquil mental space. They help guide awareness gently towards sleep. As we drift to the end of tonight's quiet journey, let your breath remain slow and unhurried. Failed stars, floating in the dark, continue their soft wander through the galaxy. They never blazed with fusion, yet they carry a warmth that endures across cosmic ages. Their gentle glow drifts like a memory, like a thought slowly softening into sleep. In the stillness between bright suns, these quiet wanderers move with a patience far older than starlight. They glide through the dark like embers that never needed to burn to be beautiful. Their faint warmth reminds us that not all brilliance is loud, and not all journeys need light to matter. Even now, in the deepest regions of the Milky Way, these unseen travelers continue their slow descent. They are the universe's softest voices, whispering calm into the endless night. Their presence is a reminder that peace exists even in the vastest emptiness. Let that stillness settle inside you, like a long, gentle exhale drifting through your body. Let the quiet motion of these failed stars guide your thoughts into softness. Feel the comfort of knowing that even the faintest objects carry purpose, and even the dimmest glow endures. Tonight, may their slow, silent drift help your own mind unwind, unwind. May their patience ease your breath. May their calm wrap around you like a warm, invisible blanket. Thank you for joining Science Sleep tonight. Rest deeply. Sleep well. Good night.